this problem, in this problem we are given a directed graph and we are given an integer s, and we would like to find a length of the longest cycle on which s lies. We need to find it by running one single DFS visit on s. There might be cases when you cannot find the longest cycle if you run DFS visit on s. It's okay. All I want you to do is to run a DFS visit on s, and whatever longest cycle you can find, return the length of that cycle from this function. So let me show you example why you cannot find the longest cycle. For example, if s is equal to 2, for this cycle we run DFS visit on 2 and assume that adjacency list contains vertices in increasing order. So first you visit 5, from 5 you will go to 6 because 6 is less than 7, and then you will discover a cycle. This cycle has 3 edges. You will record this number, this is your current length, and then you go and visit 7, and this cycle you will discover cycle, and this cycle has 1, 2, 3, 4 edges. After that you will go from 7 to 11. Notice that when you return from 8, 8 becomes black, and when you process edges, nodes 11, 12, 13, when you see 8 black from 13, you're not gonna call DFS visit on black. So cycle, this cycle will not be discovered. So you will go and visit up to here, and you will not discover cycle because you do not call DFS visit on black vertices. So the actual longest cycle, which has 1, 2, 3, 4, 5, 6, 7 edges in this graph, will not be discovered, but cycle of 1, 2, 3, 4 edges will be discovered, and it is greater than 3 edges, so your function will return 4. Now let's think about what things we need to take care of. First of all, whenever you run this function, DFS visit, how would you find length of the cycle? This is one thing. So let's write this question down. How to find the length? How do we find the length of the cycle? And especially, can we find length of the cycle in efficient way, meaning in linear time, or of v plus e time? Okay, this is one question. Another question is, what if there is another cycle that doesn't include 2 on our way? For example, what if we have edge from 8 to 7, then we have another cycle, but this cycle doesn't include 2 exactly. So, and we might actually have a longer cycle here, 1, 2, 3, 4, 5 edges. You see, if I add this edge to the graph, then 5 edges actually is greater than 4 edges on this cycle, but this cycle doesn't include 2, and our s is 2. And we need to watch out for this case. So we need to watch out that cycle includes s. How can we check it contains s? How can we check it efficiently in constant time? Well, this question is easy to answer. I'm going to answer it to you right now. When you run DFS and you encounter a gray vertex, check if this vertex is the vertex from which you started running DFS visit. How do you know that? Well, because when we start running DFS visit, parent of this vertex will be itself, so parent of 2 will be 2. You can easily check if parent of 7 is 7, and it will not be 7, and hence this cycle doesn't include our original vertex. So only pay attention to gray vertex that is the original vertex. Let me run this, show you something that we're going to use. In this problem, it is better to use not only parents array, but also distance array. Just as in BFS we use distance, here our distance array will not calculate the shortest path length, but it will calculate the length from the source to the current node correctly. We update distance in parent just as we update it in BFS. Whenever we encountered vertex for the first time, we update its parent and also we update its distance. So let me show you. So right now we're starting it on 2. It's gray. We set it to gray. Its parent is 2 and distance is 0. We set our original vertex parent to 2 and distance to 0. And after that we call it on its child, DFS-visit on its child if it is white. It is white, so we call in DFS-visit on 5, set it to gray, and set parent of 5 is 2, and distance of 5 is equal distance of parent plus 1, which is 1. Again, two integers that I show next to the vertex, first one is parent, another one is distance. From 5 you're going to call it on 6, so 6 will be set to gray, parent to 5, and distance is 1 plus 1 is 2. After the 6 you will discover 2, which is gray. That means if this vertex is gray, it's in adjacency list of 6. That means that there is path from this vertex to 6, and this edge concludes the cycle. So instead of backtracking this path from 6 to 2, we can calculate the length of this cycle by using actually distances of these vertices. First of all, you need to check if this gray vertex is the original vertex on which we started running DFS-visit. How do you check it? Is this vertex equals to parent of its vertex? Yes, parent of this vertex is itself. That means it is the original vertex, so S is included in this cycle. Second of all, to calculate its distance, we know that distance from the source to this vertex 6 is 2 edges. So what would be the length of the cycle? Well, the cycle has one more edge from 6 to 2. So if you add 1 to this distance, you will know the length of the cycle in constant time. So how to find length of the cycle? If you have current vertex U, this is a current vertex, and you found its neighbor V is gray, then you can calculate the distance, the length of the cycle, let me call it length, is equal simply distance of U plus 1. This would be your length of the current cycle from V to U, and UV concludes this cycle. Now you will need probably maintain an extra variable that you're going to pass as a parameter in your DFS-visit, and that would be current max length. Current max length. Current max length should be initially probably set to -1, because as soon as you find a cycle, then this length should be greater than this number. So you update this max length to the length that you found right now. This is 3 in our case, and you continue searching. You shouldn't just return from here. You need to find the max length cycle. So you will return it back. Now you're going to set color of 6 to black and return to 5. 5 has another child, so it will call DFS-visit on its another white child, 7. So 7 will be set as gray, parent of 7 will be set to 5, and distance of 7 is 1 plus 1 is 2. 7 will first call on 8, so because it is white, so gray, parent of 8 is 7, and distance of 8 is 2 plus 1 is 3. After that, 8 will find a gray vertex which is 7, but 7 and its parent are not equal, so it will ignore this cycle. And then 8 will find this cycle, edge to 2, and 2 and parent of 2 are equal. That means it's our original vertex. That means that we need to update maybe a length of the cycle. Let's calculate the length of this cycle. Distance of the current vertex is 3, plus this edge 1 is 4. Is 4 greater than current max length? Yes, it is greater, so we need to update current max length to 4. And after that, we'll be done with 8 and can set it to black. After that, algorithm will run to the next child of 7, which is 11. It will set 11 to gray, a parent of 11 to 7, distance to 3. After that, it will set call DFS-visit on 12, a parent is 11, distance is 3 plus 1 is 4. Parent is 12, distance is 5. At this point, it will discover node in adjacency list, but it will be black, so it will not call DFS-visit on this black node. It will return. After that, black, 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 returns to its parent, which is 5. 5 will be black. Return to its parent, which is 2. Parent is 2. It will return. It will be black because it doesn't have any more children. And after that, you can return your numbers stored in current max length as a result of your algorithm.